Okay, now we're going to take a look at one very important class of chemical reaction that occurs in aqueous solution. And this is known as a precipitation reaction. Precipitation reaction, we can abbreviate this as PPTN. Precipitation and then reaction would be rxns. So these are my abbreviations that I use quite frequently. Feel free to use them yourself. You may not see them in your textbook or other places, but I will use them quite a lot. So first of all, what does precipitation mean? What does it actually involve? Well, precipitation reactions involve the formation of a precipitate. And precipitate we abbreviate as PPT from a solution. Okay, and what a precipitate is just a solid. And a solid is nothing more than something that is insoluble, but does not dissolve in that solution, an insoluble substance. So if you mix two solutions together and you see a solid being produced, that is a precipitation reaction. Okay, so for example, if you have something like the reaction shown below. So in this reaction, we're combining two aqueous solutions. So we have sodium iodide, which is in this container here. We have lead 2 nitrate, which is in the beaker that's sitting down, and they're both, oh, that's just placed on the table, sorry. They're both aqueous solutions. They both are clear, they're colorless. You mix them together, and what you actually see is this yellow solid being produced. Okay, obviously now we can refer to that solid as a precipitate that we observe in the solution. And what's happening here is that this is an example of a double replacement reaction, okay, where the lead and the sodium swap places with each other. It's the lead and the sodium. They're going to change places. The lead then combines with the iodine to make lead 2 iodide. And that is the solid. That's the yellow solid that's made. The other combination, the sodium and the nitrate, makes sodium nitrate. That is just the remaining solution that's in the background. Okay, so this is an example, really good example of a precipitation reaction where we see the formation of a solid when you mix two aqueous solutions together. So how do we know, first of all, that a precipitation reaction is going to occur? How can we predict what the precipitate is going to be? Well, we're going to use a set of guidelines known as the solubility rules or the solubility guidelines for ionic compounds in water. So now we said before at the beginning that water is a good solvent for things because it tends to dissolve most things. Why does it do that? Well, water is a highly polar molecule. If you remember back from the earlier sections, we know we draw the Lewis structure for water. We know that it is bent. We know that the oxygen-hydrogen bond is a highly polar bond with a dipole pointing in that direction towards the slightly electronegative oxygen. The H is going to have a slightly positive charge. You have 2 dipoles here, 2 bond dipoles. The overall net dipole then leads in this direction from the H's at the bottom to the O at the top. The water is polar. And what this means then is that water will dissolve other polar things or other ionic things. Okay. So that simple statement is a reflection of a simple rule in chemistry known as like dissolves like. And we can use that to apply to lots of different situations, not just in chemistry, But if you have a polar solvent, if the water is a polar solvent, there's a net dipole in it. That's the thing in yellow. It will dissolve other things that have a similar or a like polarity. So that means a polar solvent like water will dissolve, will mix very easily with other polar things. Okay, so like dissolves like, same polarity, or it will dissolve ionic compounds because ionic compounds are as polar as you can get. These are extremely polar. They're so polar, in fact, that they're just ionic. Okay, so that's the reason why it's considered a really good solvent for most things, because it's polar. We can apply the like dissolves like rule. So how do things actually dissolve in water in the first place? Well, if you have something like sodium chloride, for instance, if I have my NaCl, which is a solid, and I add it to some water, as we talked about before, what will happen here is that this sodium chloride will undergo dissociation to form a sodium ion. We'll get the chloride ion in solution, right, so they're aqueous. And what actually happens to the salt here, this crystal, the salt crystal? Well, what we physically see, right, this is my H2O, I add my pinch of salt to it. It dissolves, obviously, so the salt dissolves when I add it. And what that looks like from a literal perspective is that it looks like the salt disappears in the solution. Okay, but does it actually disappear? And the answer is no, because what happens is we can see the salt crystal, but when it dissociates into its ions, we cannot see these ions. These are way too tiny. So it looks like it disappears, but it really doesn't. These ions that are formed actually get surrounded by water molecules in a predictable fashion because that's the polarity of water. And that process is known as hydration. So hydration happens when the ions become, when they get surrounded by a water molecule. So for example, if I have my Na plus over here, I can predict that the slightly negative oxygen will want to be associated or become close to, negative O, will want to be attracted to the positive Na plus, right? That makes sense. Opposites attract. And that's exactly how all of these water molecules will want to arrange themselves around that positive sodium ion. That's happening all the way around this ion here, right? And this is a better example shown in this case. So here, your sodium ion is hydrated. Well, the same thing is happening with your chloride ion. If you have your Cl, the minus charge, well, then the slightly positive H's are going to be oriented close to the negative chloride ion, if opposites attract. And the chloride ion gets hydrated as well. Okay, so there's a process of hydration occurring, where the ions get surrounded by water molecules, and that separates the ions from each other, and that manifests itself in the solid, the ionic solid, actually dissolving in that solution. Okay, so hydration is that specific example when water molecules, okay, surround the individual ions. That's a specific example. The general name for that process where a solvent surrounds ions is called solvation. This is when a solvent surrounds these individual ions. And hydration is a specific example of solvation. Hydration now involves a specific solvent, which is new. Solvation is for a general case. When you're talking about any solvent, hydration is specific. So water as a solvent. Okay, so essentially they mean the same thing, solvation and hydration, but hydration is specific for having water as your solvent. So as you probably know, we've talked about this a couple times, salt, NaCl, you know this from experience, right? Sodium chloride, is soluble in H2O. How do we know that? Well, we know that from experiment. You do this at home, you know that it's soluble in water. What about any other ionic compound? How would we know that they are soluble or insoluble in water? Well, we can do the same thing. We can try each of them, try to dissolve them in water, and if they disappear, they're soluble. If they don't disappear, if they stay as a solid, that means that they're insoluble. So all of that data has been collected, all those observations have been made, data collected, and they've been summarized in what are known as solubility guidelines for your ionic compounds in H2O. Okay, so what we're going to take a look at now is we're going to take a look at these solubility guidelines, which are sometimes called solubility tables. And we're going to see how we use these to identify whether a substance is soluble or not soluble in water. Again, this is specific for water, for aqueous solutions. We'll sometimes see the term solubility, and solubility means it's defined as the maximum amount of solute that can dissolve in a given amount of solvent at a particular temperature. That term is used quite a lot when it comes to talking about precipitation reactions and just things dissolving in general. So that's what it means if you see it in your textbook and other places. All right, so let's see how we use these solubility guidelines to determine the solubility of a substance. So we'll take a look at two examples right now well, maybe we'll take a look at a few others. Let's take a look at NaCl. We'll take a look at calcium carbonate, CaCO3. And then we're also going to take a look at AgCl. And then we will take a look at potassium. Well, we'll do potassium sulfate, A2S. Okay, so what we're going to do when you have your ionic compound, you're going to look at these tables. There are two parts to the table. First, it tells you about general rules for soluble compounds, things that dissolve in water, that are water soluble. And the second table looks at insoluble compounds. These are generally things that are insoluble. So we're going to look to find out ions in each of these. So the first thing that we need to do is to figure out what ions are present in your ionic compound. So the ions present here are Na plus and Cl minus. And we're just going to look for these in our table. So let's see. First rule here. Compounds containing an alkali metal cation, lithium, sodium, potassium, rubidium, cesium, or ammonium, these are always water soluble, no exceptions. So anything, in other words, anything that has lithium, sodium, potassium, rubidium, cesium, or ammonium is always going to be soluble. So sodium chloride has the sodium ion, which is here. That means it's soluble in H2O. Very simple, right? No exception. Anything with sodium in it, always soluble. If I take a look at the second one, so calcium carbonate, right? This has a calcium ion and it has a carbonate ion. So this would rely on you being able to recognize your ions and the polyatomic ions. Okay, so we look to see any of these ions in our table. Well, calcium's not here. We don't see calcium or carbonate here. We don't see calcium or carbonate. We see calcium over here, but that is in when there's sulfate present and we don't have a sulfate. So let's go to the second table then for our insoluble. So now it says compounds containing the carbonate ion are generally water insoluble, meaning it will not dissolve. Okay, so generally things with carbonate in it are going to be insoluble, except if those carbonates are combined with these, which are the same ones that we saw up here. So in calcium carbonate, we do have the carbonate. Is it combined with any of the group 1 metals or ammonium? And the answer is no. So that means that this then would be insoluble in water. Okay, so it has carbonate in it. and carbon is combined with calcium. Calcium is not one of the exceptions, so insoluble in H2O. Look at the next one. I have silver chloride. So this contains a silver ion, Ag+. Got the chloride, Cl-. All right, so let's see. If we jump down here, we can see compounds containing the chloride, okay, are generally soluble. Let's see if there are any exceptions. And there does look like silver chloride is an example, is an exception, sorry, because the chloride is combined with the silver. So that means this then is going to be insoluble. And then our last one, potassium sulfide. We just have the potassium ion, K+. Let's get the sulfide 2-. All right, so let's see. And you can look at it from a couple different perspectives. All right, it's got potassium in it, so it's always going to be soluble, no exceptions. So this will be soluble based on the potassium ion. If we look at the sulfide ion, which is the other thing, we can see sulfide down here, the S2-. Generally, your sulfides are insoluble, except when they're combined with the group 1, right, like potassium, for instance. So it still is going to be soluble. So that's the way you want to determine the solubility of your ionic compounds using the solubility tables.